grade 11s, you're here with me, Megan, on my second ever live show here on Mindset Learn Extra. Grade 11s, do you know what you're doing today? Do I hear refraction? Yes, it's all about light, and it's kind of cool because it's everything we see today. Everything that you look, if you look in front of yourself, you can see your hands. That's all with light and how it's got to do. And John and I are going to be here with you for a whole hour, and I know you're going to ask me, where do I get it? How do I? So I'm going to tell you. If you want to post on Facebook, our Facebook page is facebook.com/learnextra. Or if you want to download all the notes and be a little nerd like myself, I know you want to go to our website at www.learnextra.co.za/live. And you can hit us up on our Twitter handle @learnextra. So enough of me. I'm going to hand over to John, and we're going to discuss all about refraction.
Megan, thank you so much. Great to be with you this afternoon. Guys, I wasn't due to be here. Unfortunately, Tracy, the smaller one, she has a migraine. And that's also to do with light, because light isn't getting through to the eyes properly, and it makes you feel a little bit dizzy. So you've got me for the hour. Let's get into refraction, a really interesting topic. And here's a question that I want to ask you to think about before we get into the detail of refraction and properties of light. How do you think you're able to see an object? So let's pretend for a minute, and let's say that you take a glass of water and you put it on a desk in front of you. How is it that you're able to see this glass of water? Even where you are now, as you're watching from the screen, how are you able to watch and to see me? Think about it. Let's try and see how we're going to do that and work it out as we go through this lesson. So let's see what we're going to cover today. And the first thing we're going to say is we're going to discuss important facts about light. So that's really important. Light is such an interesting topic, and there are so many interesting facts about light, things that you can ask. So, Megan, can you sort of think about some interesting things? Well, how does a rainbow form, for example?
Exactly. Well, that's all about what we're going to discuss. And all the particles that you see are according to light in a rainbow, and that's because of all the colors in the light. Actually, light is made up of so many colors, right?
Absolutely.
Yeah.
Hey, you're showing me up here. but guys, that's what it's about. It's looking around us and seeing different things. There's some phenomenal things about light that we want to talk about. And maybe you don't know that some of the things that you're even finding and instruments that you're using in everyday life now depend on light. Of course, the television does. But did you know that a lot of phone communications, not talking about cell phones now, depend on light as well? We'll come to that a little later. So what else are we going to talk about? We're going to zoom in on the definition and explanation of refraction of light. And we're also going to link that to a concept called a refractive index. Now, we'll get to those definitions shortly, but let's start by having a look at some interesting things about light. And I'm just going to go through some ideas about light and just tick them off. If you get the notes, you'll find that these are listed there. Now, one of the things that I find quite amazing about light is that although we think about it as something that's essential for life, and it is, without light, there would be no life, because light makes photosynthesis happen, and without photosynthesis, we wouldn't have food, and we wouldn't have oxygen, and we'd be really sorry. I'm sure you'd agree with that. So really think about the importance of light. Now, what do we know about light and the importance of light is that light travels really quickly. You will hear it about people talking about it. Hey, we traveled at the speed of light. Astronomers measure the distance between objects far into space by saying that object is so many light years away from us. It's saying that you'd have to travel at the speed of light for a whole year or a whole 3 years to get to there. So I hope you can see that there is a lot about the speed of light. The speed of light is the fastest anybody can go. Well, Einstein told us that in his theory of special relativity. And he actually said that when you approach the speed of light, strange things happen. Like things get shorter and time gets longer. We won't go into that. What's the speed of light? You need to know this. You need to know that the speed of light is 3 times 10 to the 8 meters per second. And that's a really big number. That's 3 with 8 zeros behind it, and that's all happening in 1 second. Perhaps what you didn't know is that all other radiation that is like light, electromagnetic radiation, also travels at 3 times 10 to the 8 meters per second. So the television waves that we're broadcasting from here in the studio are traveling up to a satellite and coming down to your dish at 3 times 10 to the 8 meters per second. That's incredibly fast. Thousands and thousands of kilometers in 1 second. So where does light come from? Well, in studio, we're surrounded by lights. There are a lot of bright lights. And all of these objects that are emitting light, giving off light, they're a source of light. We say that they're a luminous source. So the sun, a candle, a torch, a light bulb, those would be all luminous sources of light. The terminology here is really important. So you need to remember this word, luminous source. So it projects light out. It radiates light and produces it. So what we need to recognize is that when light comes out from a luminous source, it can bump into other objects around us. And so what happens as light bumps into these objects? Well, the first thing we recognize is that the objects could be transparent. So if we had a light bulb, and we say that's a little light bulb, and light is shining out from it, it's traveling through air. And air is transparent. Light will move through the air. And it won't block it, it won't scatter it, it won't cause it to change direction, it won't do anything to that. We say it's transparent. It describes what happens when the object that transmits light with little or no diffusion or scattering. Diffusion means spreading out. Scattering means spreading out as well. But they're different in that sense because they're involved with slightly different meanings. When you scatter a light, what can happen is you can get different colors of light being produced. But we're saying an object is transparent when there's none of that happening. There's no change in direction or in type of light or intensity of light through scattering or because the object is transparent. But what about translucent? Translucent, it's kind of milky. It's kind of allows a little bit of light through, but doesn't allow all of the light through. So if you think about it, something that is got a colored plastic would be considered to be translucent. A cloth even could be considered to be translucent if it's fine enough. You can kind of see through it, but you're not entirely able to see through it. So translucent describes objects that transmit light, and when we say transmit, we say it allows light to travel through. It allows light to pass. And in this sense, it's passed through it. But diffuses or scatters the light as it passes through. So if we think about that, what's happening is we get some change in the type of light or the strength of light because of it passing through a particular object. The last point that's really important is if an object is opaque, it describes what happens when that object absorbs, scatters, or reflects light and does not allow any light to pass through it. So, if we take an example, the pen. The light from the studio is landing on this black pen as it is on my green shirt, and it's not allowing it to pass through it. Can you imagine if it allowed it to pass through it? You'd be able to see into me. You'd be able to see right into my body. Well, fortunately, our bodies also are opaque. They reflect, scatter, and diffuse light off that surface. Otherwise, you'd have like X-ray vision, be able to see into the inner workings of my body. Wouldn't that be cool, hey? So you could look right inside and see what's happening. But no, we don't want that to happen. That doesn't happen. An opaque object light falls on it, and three things happen. Some of the light, the energy of the light, is absorbed. Now, if you can tell this is what happens if you leave a black object, even a cloth or a block covered in black paint, you leave it in the heat of the sun on a sunny day, and you leave it for a while, what will happen? You will feel that it gets hot because the light from the sun is radiating energy and it's building up heat. Some of that energy is absorbed into the body and making it hot. It's not only light of the visible spectrum, but also of infrared that's being absorbed, giving the object heat. We know that if you go into a black car, it's usually, unless you put the air conditioner on, a lot hotter than a white car. So objects absorb, but the other thing that it does, it reflects. Now, that means that light coming from the studio light here travels to the pen, and it bounces off the pen and back into the camera where you can see it, or back into my eye where I can see it. And so all of these light beams are being reflected, and as a result, I can see in front of me an image of the pen. And you can see an image of the pen on the camera because light is exposing and showing you the shape of the pen. If there was no light, you wouldn't be able to see it. You would just see a black screen. We don't want you to see a black screen because we're looking at something that's opaque. Okay, so the reason we see objects, the reason we can understand and see the world around us is because opaque objects reflect light. Very important concept for you to understand. Okay, Megan, are there any questions so far?
No, I haven't got anything. All they're saying is, wait, let me actually just check. It says enjoying the show. Nonsipo says enjoying the show. Can we classify sunglasses as translucent?
Okay, excellent question. Now, sunglasses, depending on what they are made from, there are different types of sunglasses. Some of them are Polaroid sunglasses, and they do something really special to light.
My dad has a pair of those.
Yeah.
When you look at the sea, then you can see the different colors.
Yeah, that's right. It takes away much of the glare. There's a very special characteristic about Polaroid sunglasses that change the light in a very particular way. I don't want to go into the detail of what that does. We say they polarize the light. We won't go into that. But other normal types of tinted glass, we would say they are translucent because the light, you can look through it, you still see the image of the world around it. It looks a little bit different to what you would do on a clear day. Without sunglasses, just takes down the tint. So you're absolutely right in terms of that. Okay, let's go quickly. We've done this explanation, but I just wanted to draw it as a diagram to recognize if that's a surface, three things can happen when light hits an object. One, if the light comes along here and it's of a particular nature, it can be absorbed. That means that some of the wavelengths of the light will be absorbed and some of them will be reflected. Okay, so what we're saying here is that it goes into the object, into the surface of the object, and it interferes with the chemicals, with the molecules on a molecular level. Light getting in on that surface can interfere, that energy can be absorbed to make the molecules do different things. And in grade 12, you'll learn a little bit about that it can actually on a metal surface kick out an electron. But we're not going into that today. We're saying light is absorbed, it can be reflected. That means it can bounce off it. And so if we were looking at this object and we saw yellow light coming from it, even if it was white light being shone on it, then we see it as a reflected yellow, then we're going to say that this object looks like yellow to us, even though it is being exposed to white light. That's an example of absorption. The reason you're seeing my shirt as being green is because the light falling on it, the white light falling on it, is absorbing all the frequencies other than the frequencies that make up this particular color. Whereas the black object that you're seeing here, the pen, it's absorbing all the colors of light and reflecting very few. And that's why, in fact, you're seeing a black object. So when we have a black surface, very little reflection actually takes place. White object, lots of reflection. Right, refraction. We'll come to that. Now, the last thing, 2 minutes, even less. What will happen is if we get light going to a surface and passing through a surface, it could change its speed. And when it changes speed, we say that it has been refracted. Right, Megan, I think we've come to the end of this introduction.
Yeah.
So, time for an ad break.
I think so. Mindsetters, grade 11s, please just go get some water or go to the bathroom or text your friend to come and watch our live show all about light and refraction and how we see what we see in everyday life. So if you have any questions, please put them on Facebook for me at facebook.com/learnextra. We'll see you just after the ad break. Welcome back, grade 11 Mindsetters. You're here with me, Megan, and John in the studio. We are here discussing refraction, which is all about light and how it works. And earlier we were discussing about rainbows, and I know you guys are really interested in that. But we actually have a really, really good question, which I was talking to John about now. Lumandulu says, is light a particle or a wave? John?
Well, Megan, you know what? This is a question that's not really relevant for today, but I'll give you the short answer. It's been a puzzle to physicists for many years. And what we accept now is that we can't say it's definitely a wave or it's a particle, so we've kind of put them together, and we've said there are times that light behaves like a wave, and there are times that light behaves like a particle.
Okay.
So we call it the wave-particle duality.
Okay, cool. Well then, and then Aladil asked if we're going to be taught about Snell's Law, but we are going to do that.
Absolutely. If you take a look at the notes, Adil, make sure you get them out so that we can show you through Snell's Law. We'll introduce it this week, and we'll do some calculations in the next couple of weeks on Snell's Law as well. Okay.
Okay.
So, can I carry on?
Yeah, go for it.
Okay, good. Right, so let's go. Guys, we want to just cover the important laws that you need to know. And I'm going to rush through this first one, which isn't refraction, but reflection. Because remember what we said. When a beam of light strikes an object, it can be absorbed. We don't have a law for absorption at school level. There are complicated physics and chemistry things that happen in terms of absorption. But reflection is the second thing that can happen. Now, there are laws of reflection that you need to know. The reason when you stand in front of the mirror, you see yourself and looking beautiful is because of the law of reflection. If it wasn't for the law of reflection, you would see a terrible image. But here's what happens. So let's go through it, and it helps us introduce some important ideas. If this is a surface, so we have a surface here, which I've drawn with a broad white line, and we have something coming into that surface. I'm going to just go over it in green, a straight line representing a beam of light, and we're going to say that beam of light is called the incident ray, and we use an I to represent incident ray. Then what will happen is that at the point that it touches the surface, at this point, that point, there is a line which we can draw perpendicular. In other words, at 90 degrees. At 90 degrees to the surface. And we call this line, often drawn as a dotted line, the normal. So the normal is a line drawn perpendicular to any surface. So if that's my surface, the normal will be at 90 degrees. If it's standing like this, the normal's at 90 degrees this way. It's an imaginary line, people. It doesn't exist. We just draw it, and that's why it's dotted. Then the next thing that we're going to say is that there is another line that comes out, and that's the reflected ray. So we've got the incident ray, we've got the reflected ray, and I have an R on that. Incident coming in, and reflected meaning going away. So it's reflected and it's leaving. Now, what's important here is these angles. This angle theta I is known as the angle of incidence. And this theta r is known as the angle of reflection. And the law of reflection says two parts. Firstly, that the normal, the incident ray, and the reflected ray will all lie in the same plane. So if you imagine it, what's it saying is as the beam comes in, it doesn't suddenly skew off at an angle. As the beam comes in, it carries on in the same direction as it was. You could take a piece of paper and you would be able to have the incident ray and the reflected ray going in the same general direction. That's what it's saying. The normal, the incident ray, and the reflected ray are in the same plane. Very important part of the law. Second thing that we're going to say is that the angle of incidence, and we've got it down here, they're all in the same plane. I've explained that. But now the point is, the angle of incidence is equal to the angle of reflection. So on this diagram, we can say theta or phi 1 or phi I is equal to theta r. Okay, the angle of incidence is equal to the angle of reflection. You must learn that. And when you draw diagrams, you must measure those angles and make sure that they're equal whenever you're doing reflection. Okay, now we're going to move on to a couple of questions. And I'm just going to do a couple of them. They are in the notes, so let's just go through it. How do we know that light can travel through a vacuum? Megan, any idea?
Sure, you got me, John. Please
Okay,
tell me.
quickly. Where's the sun? Out in space.
Mm-hmm.
And what else do we know is in space? Is there air in space? Can people breathe in space?
No.
No. So space is a bit like a vacuum. There is no air. You can't even have sound traveling in space. But light travels from the sun to the earth. So we know that light travels in a vacuum. The reason? Because light comes from the sun. Light goes from the sun to the earth. And that's the simplest form of being able to explain that, or the simplest answer. What is the difference between a luminous object and an illuminated object? Very important question. Luminous, remember, is a source, something that gives out light. Illuminated is one in which light has been shone on, and it itself isn't generating the light, but is simply reflecting light. So at the moment, I'm illuminated by the beams of light coming from the studio lights. I'm certainly not a luminous object. No, I'd have to be a bright star to be producing light. I don't want to burn up just yet. So I'm not going to be a luminous object. I'm going to be illuminated. Okay, you got the difference between those. Right, let's move on. What happens? Very quickly, what happens when light falls on a mirror? Well, what do you think, Megan?
When
light falls on a mirror.
What happens?
Yeah, what happens to the light?
You see yourself in a
Yeah,
mirror.
you see yourself. So is it absorption, reflection, refraction?
Reflection.
Reflection, excellent. So what about a black cloth? Now, I think you need to think carefully about it. I did give it away earlier. What do you think happens when light falls on a black cloth?
Illumination.
Okay, so let's have a look at it. What we need to recognize is that light is coming in onto the black object. Okay, so if that's the black surface. Is any light traveling out when we see black?
No.
Well, actually, no. Guys, that's an important thing. White objects reflect all of their light. Black, we see black because there's no reflection. Okay? So if light shines onto a black thing, an object, a black cloth, there is absorption. And there is no reflection. Now, if it was a very thin piece of lace,
But that's like when you wear black clothes, then
Correct.
you get hot. You really,
that's
really
exactly
hot.
it,
Yeah.
because it's absorbing it. There was a very famous golfer, South African golfer, who won many Grand Slams overseas. He came from South Africa, Gary Player, and when he went overseas, he wore black. He was known as the Black Knight because he got so cold from the sunlight overseas, he kept himself a bit warm. Okay, so there's no reflection, there's just absorption. Window glass, well here, window glass, there are two possibilities. Depends on the angle that the light shines onto the window glass. Most of the light is going to go straight through. So if it passes through, then we say that it's changing from air to glass, it's changing its medium, and what that will mean is it will change speed. It will no longer travel at 3 times 10 to the 8 meters per second, and if it changes speed, we say that it undergoes refraction. And that's the point of this lesson. We want to get to the idea of refraction. Change in speed is refraction. What can happen if light shines on a glass at a certain angle, you can sometimes get like a shiny reflection. But that doesn't happen very often. The main thing that's going to happen on window glass is you're going to get refraction, because window glass is transparent, mainly. Okay, so I hope that's helped you clarify some ideas. I just want to go to one last thing about refraction, just to get it into your head what refraction is about. And I'm going to do a little demonstration. We'll do this quickly, and then we'll do one more example in a second. Have we got time for this, Megan?
Yeah, definitely. Go for it.
Okay. Right. So let's go. If we take a block now, let's say that this is a glass block. And I want to show you the effect of refraction. So this is a glass block. And we're going to say here is some air. Now, let's be very clear. We're going to say there's a beam of light traveling in. Guys, beam of light, you can do this for yourself. You can take your torch, you can get a block of glass or block of perspex, take your torch and cut a cardboard shape to it. So it's just a thin little beam that travels through the cardboard. Put the cardboard, sellotape it on top of the torch and allow the little beam to go through. Make it a dark room or do it at night time, and you'll see the beam of light travels through the block. Now, if the beam of light is put at this angle, at 90 degrees to the surface, the beam of light will in fact just go straight through it. But what I want you to understand is that there is still a change of speed here. Here it was traveling in air, here it's traveling in glass, and it slows down because the particles are closer together. So it slows down here, and here it goes back to air. So it was traveling slowly, it will speed up. This change of going from fast to slow to fast again is called refraction. Now, when we have a line like that, a beam of light that is at an angle like that one, then there's an additional effect. We will see that the beam of light doesn't go straight through. It will bend. And that's what you need to be able to explain. The bending of light when it travels through a transparent object. Now, depending on how those particles are packed together will depend on the degree and the amount of refraction that takes place. The person that described that was a man called Snell. Developed Snell's Law, which we'll come into a little later. But this is more as important as Snell's Law. I want you to get this right, because then you can do the calculations. Drawing the diagrams first is the most important thing. Now, we have an angle of a normal, like we had with reflection, that is at 90 degrees to the surface, and we'll call that the normal. It's not a very straight line, but I just want to put it there as a dotted line for the moment so that we can see it like that. So we have a normal, and this angle here between the normal and the incident ray, this is the incident ray, so this is going to be the incident angle, the angle of incidence. Now, if the glass block is not very shiny, then you will find that most of the light will continue into the block. If the glass block is shiny, we might get some reflection at the surface. Let's pretend that there's no reflection. We're going to say that all of the light carries on into the block. What's going to happen? On this side, on the glass side of the block, here, we find a very interesting observation. What happens is that the beam of light bends, and it bends in a very special way. Because it's moving from going fast to going slow, it bends towards the normal. Let me show you that. It doesn't carry on in the direction it was going to go. It doesn't continue on the yellow line. That doesn't happen, okay? But it has actually bent towards the normal. In other words, it's made an angle here that's smaller. It's bent closer to the dotted white line. This angle now between the normal and the green line, the normal and the green line, is called theta r. Theta r is the angle of refraction. Okay, guys? So let's cover this carefully. If an object, if light is moving into a transparent object, strikes it and is refracted, and it slows down, then the beam of light will bend towards the normal. Very important. What you'll notice is you've got to be able to draw this diagram very carefully. It went angle of incidence, didn't carry on going on the dotted yellow line, but it bent towards the normal. The angle of theta is not the same as the angle of refraction. The angle of incidence here is much larger. The angle of the refraction is smaller than the angle of incidence. So bear in mind, that's what's happening. When it's going from fast then to slow, the angle of incidence will be greater than the angle of refraction. And again, I know it's confusing because there's an R here and there was an R in reflection, but we need to understand that very carefully. I think we're coming up for a break, but while you go to the break, what I want you to do is ask yourself, what happens when this beam of light strikes this surface here at the bottom? I'm going to highlight it in pink. Okay? So when the light beam is going from glass to air, what do you think is going to happen now? When it's slowed down, it moved towards the normal. What do you think is going to happen? See if you can draw it. Just get a sketch out, see if you can draw what happens, and we'll come back to completing this after the break.
Okay, cool. Thanks, John. I hope you guys carry on posting your questions. I see you guys are very, very, very keen on today's lesson. And so am I, so I'll see you after the ad break. And don't forget, post your questions on facebook.com/learnextra. I'll catch you guys after the break. Welcome back, grade 11s. You're here with John and I, and we are discussing all about light and refraction. And I see that Colleen Jackets has a question for us. She says, does a white cloth or any other color except black also absorb light?
Okay, very good question. Now, we did extremes. Guys, white objects on the far one end of this color spectrum, white objects reflect all the light. It hardly absorbs anything, okay? Black objects, on the other hand, absorb everything. Things in between, like green or red or blue, they absorb certain frequencies of light and reflect the frequencies that you can see. So you see a green object because it's reflecting green light. All the other colors of light are being absorbed. A blue object will only reflect blue but will absorb all the other colors. Hope that makes sense.
Yeah.
Megan? Okay. Shall we get back to my challenge?
Please do.
Okay. So what we've got here is, remember, we're dealing with that glass block, and we're going from glass into air. And what we're saying is here it was slow, and here it's faster. Light is able to travel at different speeds. What's going to happen? In the same way as we did before, we're going to draw in the normal. At 90 degrees, let's just get that a little bit straighter. This one at least. And I'm going to just erase it a little bit so that we've got it more dotted. And I'm just drawing it freehand at the moment. If you had a ruler, you'd be able to draw it much more accurately. Now, this angle inside the green block, inside the glass block, is still known as the angle of incidence. Wherever there's a medium, a change in medium, a barrier, this is the change in medium, then there's an angle of incidence. Light is striking, that light ray is striking at that position. What's going to happen? I want you to notice that it will not carry on in the same direction. So it's not going to carry on down there like that. We know that that's not going to be the case. What's going to happen? And I like to put that line in, use a ruler and draw a dotted line in, because that's where we might expect, if there was no barrier, that's where we would expect the light to travel. If there was no surface, there's no interface between glass and air, we would expect the light to carry on going straight. Now there's a barrier. It's not going to do that. It's going to speed up. So what does it do? It bends away from the normal. So instead of going there, it's actually now increased its size. So can you see here that the angle of refraction, theta r, is going to be greater than the angle of incidence? Now, we've spelt out these laws of refraction in detail in our notes. So please make sure you understand the drawings and you understand the statement. I'm not going to go over those, but just understand them. When we're moving from air to glass, where the particles are closer together, we sometimes say that's optically more dense. And it's a very loose expression. We'll come to define that more definitely a little later. I want to do one more example just to illustrate it very quickly. But what we will say is that there's a refractive index. Where light travels slowly, fast, it will bend towards or away. You need to make sure if it's moving from slow to fast, it bends away. When it's moving from fast to slow, it bends towards. Make sure you understand how we're indicating this angle that is increasing and this angle that's getting smaller. One last thing. For a prism like this rectangular block, where the sides are parallel to each other, then the incident ray and the reflected, the final emerging ray will be parallel to each other. When the sides are parallel, then the rays will be parallel. That's not always the case, because if we go to a prism like this one, where the sides aren't parallel, let's quickly do this one. What I want to show you is that here, the light would have carried on in that direction, okay? But now it's not. And I'm going to go through it very quickly, and I'm just going to draw it freehand as well. It's going to refract over there because it's bending towards the normal. There it's bending towards the normal. That's the incident, the angle of incidence. This is the angle of refraction. This is the angle of refraction. Now when it gets to this point here, let's draw in the normal, just very quickly. And we draw the normal in as a yellow line. It's not going to carry on straight. We know that it's not going to carry on doing that. Let's just draw it in another color so we can see. It's not going to carry on out like that, but it's going to bend away from the normal. The yellow line is the normal, so it's going to increase the angle. It's going to bend away. Let's draw that in, and let's see it like that. So there we go. There's the angle of refraction. There's the final angle of refraction, and there was the angle of incidence. The angle of incidence on that side. So I hope you can see that there's refraction at both surfaces. Where it was over here, it is slowing down, and here it is speeding up as it's leaving. Now, there is one last thing about this diagram, and it is in the notes, that we sometimes use with a triangular prism, like this one, and we say that this angle is the angle of deviation. That's known as the angle of deviation. It's how much the light has changed from its original path. So along the white line at the top, it was going, now it's emerging down at the green line at the bottom, and it's changed significantly. The prism has bent the light, has changed the direction of the light. We say it's undergone refraction. Now, I want to speed up for one last thing and to define something for you. We've been talking about speeding up and slowing down, and here we come to a very important definition that we haven't encountered before. And in fact, you're the first group of learners for many years that have actually got to learn this. It's called the refractive index. And what we say, the refractive index is a measure, and it's given a symbol N. It's a measure of the ratio of the speed of light in a vacuum to the speed of light in the material. So it's not difficult. We're saying it's the speed of light c divided by v, the speed of light in the medium. So let's have a look and see, where is the light going to be traveling faster or slower? So have a look. If it's got a refractive index of 1, what is that telling us? It's telling us that the ratio of c over v, this, remember, c is equal to 3 times 10 to the 8 meters per second, divided by 3 times 10 to the 8 is going to give you 1. So that's telling you that the speed of light in a vacuum is about the same as the speed of light in air. Now, very important, the refractive index can only be a number of 1 or bigger, because you can never get anything going faster than the speed of light in a vacuum. So we can't have this as a fraction. Refractive index has to be always 1 or bigger. The bigger the number, the slower the light is going to travel at. So in a diamond, now I know diamonds are a girl's best friend, or so they say, but light traveling into a diamond reflects off the surface, but it also goes into the stone. And that's what makes it sparkle so much, because it can sparkle on the inside as well and reflect on the inside and give you lots and lots of images from there. Light travels really slowly on the diamond. So if we have a look at that ratio, have a look what's going to happen. If you put the speed of light and you make this number here really small, much smaller, you make the v small. V, make that small. Can you see you're going to get a big number, a number like 2,4 compared to 1. The smaller this becomes, the bigger this number is. And what that's telling you is that light is traveling slower in these objects. Okay, hope you've got that. Hope it's clear. What you should notice as we look at these, you'll notice that water is a refractive index of 1,3, whereas perspex is 1,5. Now, please don't get the idea that it means that gases have a low refractive index and liquids have a slightly higher refractive index and solids have the most refractive index. That's true generally, but not entirely. There are some liquids that are almost opaque. They don't allow light to travel through them, or they could have a very high refractive index. And you can measure the refractive index of something by doing an experiment, by comparing the angles of refraction and reflection of incidence. And that's exactly what Snell did. And he came up with his law, which we're going to have a look at now. So here it goes into Snell's law. I'm just going to skip through that because I want to get to Snell's law. What it says is this, that when light travels from a material with a refractive index N1 into a refractive index N2, the refracted ray and the incident ray and the normal to the incident between the materials all lie in the same plane. So guys, that's exactly the same as what we said about the law of reflection. Do you remember? The incident ray, the normal, the reflected ray, all in the same plane. That means if I shine a light down on this board like that, then the normal is going to be on that line and the refracted ray is going to be on that line if this was a surface that's going to happen. They're all in the same plane. I want you to get that idea of plane correct. Now, let's go to the second part of the law. The next thing it describes is that the angle of refraction, theta r, is related to the angle of incidence by this expression. But please don't go magoo about it. Don't think, oh dear, what have I done? What's going on? No, it's really simple. Because what we're saying is that if we have a surface, and we've got a surface like this green surface over here, and we've got a beam of light that is coming in over there like that, then remember the normal is going to be down like that. Then what we're going to say is that this angle here is the angle of incidence. Now, what this expression is saying to you is it depends on the refractive index of material 1 and material 2. If material 1 has a refractive index of, let's say, close to 1, or it's small refractive index, then we know that that means that the speed is high. Speed is high. But if the refractive index here is big, then the speed is low. And what's going to happen? Then we're going to say that we're going to get refraction where it's bending towards the normal. In other words, theta r is going to be less than the angle of incidence. Hope you've got that. The ratios will tell you that. By working and plugging into that, you can work out the unknown angles. You'd have to have one angle and the 2 refractive index to get the other angle, or you could be given 2 angles and 1 refractive index to work out the other refractive index. That's what Snell did when he originally worked it out. He measured the angles, he measured the refractive index of air, took it as 1, and then was able to work out the refractive indices of a whole range of material. Well, guys, there's a lot more that you can do with this particular equation, and we're going to do lots of calculations with them. It's important that you understand the drawings though, and make sure that you've got the ratios correct. Understand what refractive index is, understand what the angles are, and you can substitute them into Snell's equation. Very good to be with you. It's been my pleasure to talk about light. It's been fascinating and illuminating to be with you this afternoon, Megan. So thank you for being here as well.
Thank you
I've
for
really
doing
enjoyed my
today's
time
lesson.
together.
No, everyone says thank you very, very much. It was, I think all you mindsetters agree with me that today's lesson was very, very interesting. Talking
Great.
about rainbows and colors and everything. So thank you for being so interactive, mindsetters. John says goodbye. And
Thanks.
from me, I just wanted to tell you that grade 12s, your lesson is coming up next, so stay tuned. But grade 11s, you have been so cooperative and so interactive, and I've really enjoyed talking to you and commenting and everything to you on the page. Just remember, if you want to get notes, because I see a lot of you are asking me, where do you get the notes? And all these notes are available for you on the website, which is, and I quote this, www.learnextra with an X live.co.za/live.
Sorry, Megan, it's learnextra.co.za/live.
Oh, the
double live.
extra is with an X. Just don't forget, because, okay. And I hope you join us next week for our show. And that's lots of love from me to you, and I'll catch you on the flip side.